We are the Bus Lightyears. Today, we will be sharing with you our design of a standardized satellite bus. First of all, what is a satellite bus? Well, a satellite bus serves as the chassis of a satellite, carrying it through launch and into space far after the satellite separates from the rocket. These typically are designed to hold various types of satellites, as seen on the right, meaning their design can be very complex as there are multiple constraints to adhere to. To help build a better understanding of the complications in designing such a thing, we should put ourselves in the shoes of someone who actually designs them. Picture this. You're a design engineer for a reputable aerospace company, and you finally validated your design of a satellite bus to be used in an upcoming launch. However, due to administrative concerns, your boss decides to use a different company for the bus. Now, you've got to restart from ground zero, redrawing designs, restarting all structural and thermal stress tests, ensuring everything meets required codes and standards. This sort of setback is all too common in the field, where designs can make or break entire launches. If only there was a way to fix this. To help fix this repeated setback experienced by engineers everywhere, we've decided to close the gap currently in the market that exists due to a lack of standardization. Currently, teams have to design buses and satellites that custom fit to one another, meaning if changes are made to one design, the other is also affected. However, if there was a standard form factor to design against, design changes would no longer cause a domino effect of changes, but instead allow designers to focus on the payload they initially intended to design. By allowing a standardized bus into the market, customers could focus on their products and their problems, and let us handle the dirty work of integrating their design into a launch with a rocket. So, how does a satellite actually make the journey from a workshop floor to outer space? There are four major stages in this chain. First, the customer builds their payload, which gets bolted into our standardized bus structure. Next, our bus attaches to a separation system, which is essentially the mechanical latch that releases the satellite once in orbit. Lastly, the whole assembly is packaged inside the rocket's cargo fairing. Across this journey, our bus has to endure brutal environments while also being easy for technicians to assemble. During launch, it has to withstand extreme acceleration forces, violent shaking, acoustic shockwaves from the engines, and the final mechanical pop of separation. And once it reaches low Earth orbit, or LEO, it has to handle the extreme vacuum of space, intense radiation, debris, and wild temperature swings as it passes in and out of Earth's shadow. To make this work seamlessly in the real world, we designed our platform to work directly with industry standard systems, like Rocket Lab's 24-inch Advanced Lightband ALB separation system and SpaceX's Falcon 9 rocket. By designing specifically for hardware that rocket companies already rely on, we instantly eliminate huge compatibility headaches for our clients. Of course, however, these systems have their own constraints to worry about, giving us a list of requirements our bus needs to fulfill as we begin design. Looking at a bus, the center of the structure is a conical inner foundation featuring an isogrid pattern. If you look closely at the center cylinder, you'll see a network of machine triangular pockets. This is an isogrid. This pattern shaves off significant mass while keeping the structure rigid. Surrounding the cone is a flat, octagonal top deck designed for payload attachment. On the exterior walls, we integrated mounting points for deployable solar panels, orientation thrusters, reaction wheels, and star attractors. Internal radial ribs extend outward from the center cone to evenly distribute rocket launch forces. Looking at the business side, about 240 satellites in this size class are launched globally every year. About 144 of those fit our SpaceX target market, and we conservatively estimate we can capture 29 satellites per year. Because 29 units per year isn't high volume mass production like cars, traditional casting wouldn't be cost effective. Instead, this market drove us to use precision CNC machining and 3D printing, keeping our setup costs low and our manufacturing agile. To summarize our project, our standardized bus eliminates repetitive multi-million dollar engineering redesigns across the entire commercial space industry. The combination of internal isogrid core and a universal top mounting deck offers maximal structure strength alongside versatile payload integration. This entire design solves an immediate business pain point, interface directly with existing launch providers like SpaceX and Rocket Lab, and fits current low volume manufacturing capabilities. Thank you so much for your time and attention today.